Hello, this is part 4 of properties of eigenvalues. So let's now consider a square matrix, an eigenvalue of that matrix, and a number here denoted by S with the letter S. We're assuming that this number S is assumed here to be an integer number, right? So that means that S can take the value of 0, or S can take the value of 1. Well, if this number we're going to take the value of -1, then that has special meaning on what we want here. But let's see. So suppose we have a square matrix, an eigenvalue of that matrix. So that means that we have square matrix A such that A times V equals lambda V, for lambda being the eigenvalue, and V here denoting an eigenvector corresponding to that lambda. Again, I remind you of the shape of this. We have on the left side a matrix vector product, and on the right side we have a scalar vector product. So the theorem says we have an eigenvalue of this square matrix. Suppose we have an integer S, then lambda to the S power. So again, so you suppose that S is, I don't know, 3, then lambda to the S means lambda to the 3, which means that you multiply lambda times itself 3 times, okay? So lambda to the S power in the sense of lambda being the base and S being the exponent, that is a number. So lambda to the S is itself a scalar, and what this theorem is telling us is that this new scalar, lambda to the S, it's an eigenvalue of the new matrix A to the S. And so maybe we should also illustrate what does that mean. So A to the S, okay, as if S is an integer, the notation A to the S denotes exponentiation of matrices in the sense of multiplying the matrix by itself, okay, a number of times. So multiplying A in matrix multiplication S times, okay, that's what this exponent denotes. A to the S is a new matrix obtained after you multiply the matrix A times itself. So let's again use the same, let's use a different value. Say S equals 4, so A to the 4 is a matrix obtained by multiplying A times A times A times A, okay? Multiplying the matrix times itself, and so we're assuming these are this matrix square, so you multiply square matrix times square matrix, still square matrix times square matrix square, so you're multiplying square times square, and that gives you still a matrix that has the same number of rows and columns. Here we're assuming that that number is probably n, all right? And so this A to the S matrix is a new matrix, and an eigenvalue of that new matrix is the lambda S, also a new scalar after raising to a power. So one convention when speaking of powers of matrices, one convention is that when S equals 0, okay, and we say A to the S power, so we're talking about A to the 0 power, one convention is to consider this A to the 0 as the identity matrix. Remember, this is the matrix that has 1s across the diagonal and 0s everywhere else, right? And so that's in the spirit of what we had at the scalar level, right? So if we're working with scalars, we would say if lambda is a complex number, then lambda raised to the 0 power is 1. This is really 1 plus 0 times I, but that's a convention also, that the 0 exponent is 1, is the 1 in the sense of the definition of a vector space, right? So C, the complex plane, is a vector space, and this number here is considered 1 in the sense of the definition of the 10 properties required for a set to be a vector space. And so in matrices, in the space of vector space of matrices M sub n, a to the 0 by convention will be considered the identity matrix. So suppose we consider a non-trivial vector x such that a times x equals lambda x. In other words, suppose that we have an eigenvalue lambda of the matrix A with a corresponding eigenvector here denoted by x. So now let's consider the power, the 0 power in terms of matrix multiplication. So a to the 0 times multiplying that eigenvector corresponding to lambda for a to the 0 would be the identity multiplying that vector x, which gives us the vector x. But we can also think of this vector x as 1 times x. Okay, so what we have here, we want to really consider this vector equation as this matrix a to the 0 is a matrix B, and this scalar 1, consider that as mu. And so what we have is B times x equals that scalar mu times x, and this is the definition, right? The definition of eigenvalue and eigenvector, right? So mu is an eigenvector with corresponding eigenvalue x, and mu is an eigenvalue of B with corresponding eigenvector x. And so in other words, 1 is, and so the thing to remember here is that also 1 is lambda to the 0. So what we really have here is B times x equals lambda to the 0 times x, and that's precisely one particular case of the theorem that we are working with. So let's consider now a squared, which is given by multiplying the matrix times itself. Okay, so I want to make this point again. I want to emphasize that when we write a squared, this is matrix multiplication. This doesn't mean that you go to every entry of the matrix and do a direct exponentiation. Exponentiation. It doesn't mean that you raise to that power the entries. No, it means that you multiply the matrix times itself by itself a number of times. In this case, 2 times. Okay, so consider a squared as being a times a. So what happens if we're still operating with x being a non-trivial eigenvector associated with lambda? So what happens if we now so since, okay, let's write here, since ax equals lambda x, then ax equals lambda x. So what happens if we multiply both sides of the eigenvalue eigenvector equation by that matrix, by the same matrix A? So the left hand side here, this portion is going to become a square. Okay, on the right hand side, we can move lambda. Lambda is a scalar, right? And so by properties of matrix scalar vector multiplication, we can move the scalar up front, and then the matrix A multiplies x here on the right side of this vector equation. So let me work with that right side for a minute, and then we can apply the definition of a times x, right? That a times x we know is equal to lambda x, so this becomes lambda x. The left hand side stays the same, a squared times x, and so what we're deriving here is that this right hand side becomes lambda squared times x, and the left hand side we carry on is still a squared. So this is given a new form of eigenvalue eigenvector equation in terms of the matrix A square and the scalar lambda square. Okay, so that was for the particular case of the second power of the matrix and the second power of lambda. So what happens if we consider now a power, say 3? So suppose we start where we left off start with a square times a non-trivial eigenvector for ax, which is associated to lambda, the eigenvalue of a. So start with a square equals a square x equals lambda square x, and then let's go ahead and multiply in both sides of this equation by the matrix A, right? So I want to emphasize this again. All we're doing here is that we previously had a square matrix multiplying a column vector, and we're multiplying that now by a new matrix, okay? And then on the right hand side we had a scalar lambda squared multiplying a column vector, and now we're multiplying this times a square matrix, right? So you can see the dimensions do work out. On the left hand side we're still have on the left hand side a column vector, and we have matrix times scalar, that is a matrix, times column vector, that's still a column vector. So the dimensions do work out, and so turns out that this left hand side, a times a square, is something that we can write as a to the 3. That multiplies x, and then here we can do what we did before, right? Lambda squared up front. Lambda squared up front means that then we have a times x, but using the definition of a times x, that is lambda x, and we had a lambda squared that is up front over there. So this lambda squared times lambda becomes lambda to the third power multiplying x, and that's what the right hand side becomes. And the left hand side, we keep the left hand side as it was. So we have a to the third power, the matrix a multiplied by itself 3 times x, right? And so this leads to another vector equation which has the definition of eigenvalue and eigenvector. So this equation is telling us that lambda 3 is an eigenvalue of the matrix a times a times a. Okay, so what I'm doing here is illustrating the rationale behind the proof of this theorem. The formal proof is something that relies on a technique called mathematical induction, something that you can develop in more detail. Mathematical induction has something called the base case, and then there is something called the induction hypothesis, okay, and then you use both of these to prove the next, to give out the proof kind of in general terms, okay. So but I'm simply pointing out that there is an interplay between powers of the matrix in the sense of multiplying the matrix times itself and raising the eigenvalues to the same power. So if you're considering the matrix a to the 100th, right, meaning you multiply the matrix 100 times by itself, then there is an interplay that's directly related with the 100th power of the eigenvalues of that matrix.